This conference will now be recorded.
Hello everyone, the topics we are going to discuss today, that is preparation of different types of sodium related compounds. So already some compounds we have discussed that are related to sodium. Today we'll start with some more compounds related to sodium. And after finishing it, we'll also see what is the biological importance of potassium and sodium, these two metals, fine, and related problems. Sodium hydroxide, the formula you can see here, NaOH. So it looks like this as you are seeing here. If we talk about the properties, because the preparation part that we have already finished, so here we are focusing on the properties. Okay. So NaOH, it is white as you can see here, translucent. That means translucent means it is not completely transparent and it is not completely opaque. It is something in between, translucent. Then deliquescent solid. Deliquescent means it has a property to attract water, and corrosive in nature. That means if you touch it with your skin for a long time, if it is in the contact of skin, then it can destroy the skin. Okay, it is not good for our skin. So we should handle it with by wearing after wearing gloves. It is highly soluble in water, and once it is soluble in water, the solution that you get, it is basically strong alkaline solution. Okay, because of presence of HO minus ions. Melting point 591 Kelvin, and NaOH solution at the surface reacts with carbon dioxide in the atmosphere. So if you keep it open, then in the atmosphere, the carbon dioxide that is present, there is reaction with it and it forms Na2CO3, which is another sodium compound. We call it sodium carbonate. Uses of this sodium compound NaOH as a laboratory reagent. Obviously it has very significant use as a laboratory reagent when we need some alkaline solution. Then sodium hydroxide and another one is potassium hydroxide. These two are basically very common in the purification of bauxite and petroleum refining. So these are some other applications. Textile industry for mercerizing cotton fabrics. Mercerizing means if we want to increase its tensile strength, that is the capacity to take load for the fabrics. If we want to increase, then we have to do this mercerizing process in which we use NaOH solution. Manufacture of soap, paper, artificial silk, some chemicals, and for the preparation of pure fats and oils. Because when we talk about this is basically sodium salt of very large hydrocarbon chain containing carboxylic acid. So there also this compound has application. Fine. So the next compound we are now going for sodium, it is sodium bicarbonate. Look at the formula NaHCO3. Okay, so this is the salt of H2CO3. If you consider carbonic acid, H2CO3 is the formula. If you simply replace one of the hydrogen with sodium, there are two replaceable hydrogen, but if you replace only one, you get this salt which we call sodium bicarbonate. Okay, one hydrogen is still there. First we'll see preparation. How you can prepare it. The compound you can prepare by saturating a solution of sodium carbonate with carbon dioxide. So here as you are making sodium bicarbonate, which is containing sodium, so we need some starting material as a source of sodium. So which starting material we are using? We are using sodium carbonate, that is Na2CO3. Now the white crystalline powder of sodium bicarbonate, which is basically the product in this case, it is having less solubility, and as a result it can be precipitated out. So look at the reaction. Na2CO3, which is the main source of sodium, you are treating it with CO2 and H2O. Basically what we are saying, that preparation is done by saturating a solution of Na2CO3 with carbon dioxide. Now Na2CO3 solution means what? Obviously water is there. So in the equation you can see water is there, Na2CO3 is there, you are saturating it with carbon dioxide gas. You are getting the compound NaCO3, which is the desert compound. We are trying to synthesize it. And this molecule, as the medium is water medium, right? And it has very low solubility. So you can get precipitate. And this is actually, we can exploit the fact of its low solubility. As it is less soluble, we can get PPT and you can filter it out and you can get pure product like this. And it appears, this you can see in the picture, it is white powder type. After preparation, next we have to see properties. Now, not just sodium bicarbonate is the only name of it, you can also use some other names. You can call it sodium hydrogen carbonate, or if you are replacing this word, then you have to use bi. So either you call it sodium bicarbonate or you call it sodium hydrogen carbonate. Another name is also there, baking powder. Why we call it baking powder? It is called baking powder because when it is heated, there is decomposition of this molecule and bubbles of CO2 generated. And these bubbles of CO2, when it is, that is, this baking powder is used in the preparation of cakes and pastries, there, because of these CO2 bubbles, there it leaves some holes in the cakes and pastries, which is giving it this fluffy nature. Okay, light and fluffy nature we are getting because of this reaction, this particular property of NaCO3. So this is the purpose why we use NaHCO3 in the preparation of cakes and pastries, because to generate this type of fluffy nature. And this is because of this reaction. As you can see, it is basically the decomposition of NaCO3. In presence of it, it is decomposed to Na2CO3. See, it is basically the reverse of this reaction, isn't it? In the, when you have made it, you have taken Na2CO3, CO2 and H2O. You are getting NaCO3, but if you do the reverse reaction, you are now heating it. Now you are getting back Na2CO3, H2 and CO2. So this CO2 is basically responsible for these holes generated in the cakes and pastries. Application in baking cakes and pastries, obviously, as we have discussed just, as mild antiseptic for skin infection. It is very mild, it has not very high power, and in fire extinguishers. Now, if you are thinking how it can be used as fire extinguisher, let me tell you, just look at this reaction, the previous one. When you are heating NaCO3, there is production of Na2CO3, H2O and CO2. Now, this CO2, it retards it retards the fire, because for fire it needs oxygen, and if there is generation of CO2, then also it retards the process, so ultimately extinguishing the fire. And also there is formation of water, which helps in cooling the extra heat during fire. Okay, so these are the applications of sodium bicarbonate. Next we will see sodium carbonate. So Na2CO3 you have used for preparation of NaCO3, right? Now we are directly discussing this compound. So this is also generated from H2CO3. If you replace both this hydrogen with sodium atom, you get Na2CO3. Preparation. First we have to see preparation. Now for preparation of this molecule, Solvay process we use. Remember the name, Solvay process. So by Solvay process we produce Na2CO3 or sodium carbonate. Now there are some steps, carefully observe. So first what we are doing, if you look at the first reaction, number one, I'm writing here, ammonia, water, carbon dioxide. These three together, it is making ammonium carbonate, NH4 plus ion. The formula is just like Na2CO3. Only difference is that in place of sodium, now you have NH4 plus. So two NH4 plus ions are there, and CO3, two negative charge, two positive charge. If you combine it, it will be ammonium carbonate. Sodium carbonate is prepared by Solvay process, in which ammonia is converted into ammonium carbonate. So the first reaction, you can see how ammonia is converted to ammonium carbonate. Now this ammonium carbonate, second step, this ammonium carbonate, further we are treating it with H2O and CO2. This part is same. Now you are getting ammonium bicarbonate. See, it is just like sodium bicarbonate, only Na, instead of Na we have NH4. Now sometimes in some books you can find that directly ammonia, water, CO2, that will be in the left hand side of the reaction, and ammonium bicarbonate, that will be in the right hand side of the reaction. That is what I am trying to say. If you simply add these two equations, this part will be cancelled, because whatever is product here, that you are using as a starting material in the second reaction. So together also you can write this reaction. So in that case you have to omit ammonium carbonate, but it is better if you break this equation so that you can understand that there is some intermediate generated, which is ammonium carbonate. This ammonium carbonate finally converted to ammonium bicarbonate. So second step, we are getting ammonium bicarbonate. So read the first statement again. Sodium carbonate is prepared by solvent process in which ammonia is converted into ammonium carbonate. Then it is again converted to ammonium bicarbonate. Next step, what we are going to do, this ammonium bicarbonate, which is formed in the second step, reacts with sodium chloride, that means NaCl. What we are getting? Now we are getting sodium bicarbonate and byproduct ammonium chloride, NH4Cl. So let's see what is the third reaction. Third reaction is now ammonium bicarbonate, which you have made in the second step. Now you are treating it with sodium chloride. You are getting NaHCO3, and this is the other product. Now this NaHCO3, next step what you are going to do, you are simply heating it, and this reaction you have already seen in the previous slide. So in this way you can produce the final target product that we are trying to make, Na2CO3. Now here one point is very important to understand. This NaCO3 that you are getting here, I'm talking about this. Just focus on this. This NaCO3 that you are getting here, we have already seen in the previous slide that it has very low solubility, and because of its low solubility, you can get its PPT. And when you are getting PPT, I mean precipitate, you can filter it. So this is actually helping us. Its separation will be easier. So once you filtered it, you get the residue. Now this residue, when you are heating, finally you are getting sodium carbonate. So this NaCO3, because of its poor solubility, gets precipitated. Now you can easily isolate it by filtration process, and you can heat it to get the ultimate product. Now one point, remember, if you are thinking that by the same process you can also make K2CO3, no, that you can't. That is because of this third step. So you can get question related to this. Same process, if you want to apply for preparation of K2CO3, then it is not possible, because when you are making K2CO3, instead of getting NaCO3, now you will get KHCO3. Now unlike NaCO3, KHCO3, it has better solubility. So PPT generation is not possible. So PPT generation not possible means you will not be able to filter it. Isolation process will be difficult. So that is why solvent process we do not use for preparation of K2CO3. That is the difference between this Na2CO3 or K2CO3. Because of comparatively high solubility of KCO3, you cannot get precipitate. That is this point. As you are getting precipitate of NaCO3, that same thing you will not get in case of KCO3. So we do not use this method for K2CO3 preparation. So now we have seen all the steps. One more point, the ammonia which you have used in the first step. See, you have used here ammonia. Now to make this process cost effective, because you are doing it in large scale. So suppose finally if you can generate, that is recycle this ammonia from which you can start another cycle, then it will be cost effective. Okay. So ammonia used in this process in the first step as starting material, you can recover it. How? See, if you look at the third step, this ammonium chloride, from this ammonium chloride, if you treat this ammonium chloride with calcium hydroxide, you can get back this ammonia, and this ammonia you can again use as starting material. That is, you can follow the same process again. So it can be recovered. Fine. So this is the preparation part. of sodium carbonate. Next, properties. It is white crystalline solid, exists as decahydrate. See, when it is you are crystallizing it from water medium, water solution, it is associated with 10 water molecules, decahydrate. And when it is associated with 10 water molecules, we call it washing soda. Soluble in water, forms alkaline solution. When you are heating it, that is this 10 water molecule, when you are heating it, there will be loss of these water molecules of crystallization. Only one water molecule is left now. 9 water molecules are removed. Okay. Now, if you are heating it above 373 Kelvin, the monohydrate which you have obtained here, this is monohydrate. Now, this monohydrate becomes completely, there is loss of water. This is anhydrous, changes to white powder. Though there is not significant difference in its appearance, but now there is no water molecules of crystallization. And when there is no water molecule, now it has a specific name, soda ash. So what is the difference with washing soda? When you are calling, both are actually Na2CO3. Chemical properties will be same. But washing soda and soda ash, we are using two different terms. It is because of how many water molecules, sorry, not how many, I mean whether 10 water molecules are there or not. So if it is there, you will call it washing soda. But when it is anhydrous, you will call it soda ash. Reaction with acid, because it is alkaline in nature, so obviously there will be acid base reaction. When it is reacting with acid, there is formation of salt. These two are the byproducts. Uses of sodium carbonate. Washing soda is used heavily for laundry, which is clear from its name, right? It is important laboratory reagent used in qualitative analysis, volumetric analysis. Also used in water treatment to convert hard water to soft water. In hydrogen chapter we have seen its use. Then manufacturing of glass, paper, paint, textile products. So it has huge application. Okay. Now the last sodium compound, sodium thiosulfate. Thiosulfate is basically this part. If you simply remove 2 sodium, rest of the part is H2O3 containing 2 negative charge. This is thiosulfate ion. And look at it, how it appears. Very beautiful appearance. Transparent, small crystalline, which is easily visible. The crystal nature you can easily understand from its appearance. First, as usual, we will see how we can make it. You can prepare it by heating sulfur, because you need sulfur. In the molecule itself, there is sodium, there is sulfur, there is oxygen. So there must be some sulfur source, and we are directly using sulfur for this sulfur source, along with sodium hydroxide. So sodium hydroxide will be the source of sodium. 6 balance equation, you can see here, NaOH 6 4S, Na2S2O3, these are the byproducts. Now, if you want to make it in large scale, then we have to consider industrial preparation. Now, for industrial preparation, we are using soda ash. So, what is soda ash? When there is no water molecules associated with Na2CO3, that is anhydrous form, then we call it soda ash. So, soda ash and sulfur dioxide are generally used as raw materials if you want to make sodium sulfide. It is not Na2S2O3. It is not direct one step. The previous method that you are seeing, it is direct. Just one step is there. But industrial preparation, there are some steps. First, we use Na2CO3 and sulfur dioxide, and there is formation of sodium sulfite, Na2SO3. Look at this formula. SO3 2 negative and 2 sodium ion. And this ion is called sulfite. Don't write it. Be very clear about the spelling. Phite. It is not phide. So when I am writing sulfite, sulfide, or sometimes you can, it is also written like SULFIDE. So when it is sulfide or PHIDE, then it is S2 negative ion, which you can see here. It is sodium sulfide, FIDE. But when it is SO3 2 negative, now it is sulfite, SULPHITE, not DE. So this Na2CO3 sodium sulfide that we are getting in the first step, in the second step now you will boil it with sulfur. And the solution that you are getting, you will filter it, it is concentrated, finally crystallized, and we are getting Na2S2O3, but there will be 5 water molecules associated because it is in the form of pentahydrate. Just you have seen in case of Na2CO3, there are 10 water molecules are attached. But now there will be 5 water molecules attached with Na2S2O3. So that is why the name we are calling it thiosulfate pentahydrate. Okay. Now we will see the equation. So the first step, we are using soda ash as it is mentioned here with sulfur dioxide water. We are getting NaHCO3. This is the first step along with CO2. Now this NaHCO3 in the second step, it is again reacting with this Na2CO3. Though you can directly write Na2SO3, but it is better if we break the equation so that you can understand all the steps, all the molecules that are formed. So NaCO3, which is formed in the first step, now it is again reacting with this soda ash, forming sodium sulfite. This sodium sulfite, as it is mentioned here, boiled with sulfur. And when you are boiling it, finally you are getting 2Na2S2O3. Just we are increasing the sulfur atoms number. Okay. So here these 5 water molecules are not written in the formula, but ultimately it is in water medium. So when you are ultimately filtering it, you are doing it concentration and you are crystallizing it from water medium. Obviously, now 5 water molecules will be associated, and ultimately the formula is like this: N2S2O3 5H2. White crystalline hygroscopic solid. Pentahydrate of this salt has a melting point 321.4. This is boiling point. Soluble in water, but not in alcohol. And this is expected because it is ionic compound. So obviously this should be the observation. Now properties part of sodium thiosulfate is very important. Not just for this chapter, you will also find its application, or better I say its reaction, where there is other reactions in some other chapters. You will see the reaction of Na2CO3, that is the mention of Na2S2O3 in different reactions several times. So you should know its properties because it can react very large, that is various types of other compounds. Before going to its properties, that is chemical properties, let's clear the structure, because the other compounds of sodium that we have discussed, NaOH, NaCl, then Na2CO3, their structures, there is nothing very significant to discuss. But in this case, if you see, obviously there are 2 sodium and anon is H2O3. But as there are 2 sulfur, so how there is bonding between sulfur and oxygen, you should have clear idea. So that is why look at this structure. Here the 2 sulfurs that you are seeing, their chemical environment, it is obviously not same. The sulfur which is in the middle, it is attached with 1 sulfur and 3 oxygen. But this sulfur, it is attached only with sulfur. So from the point of view of this sulfur, if we see the oxidation state, it is basically 0 because it is attached to same atom. But if you look at this sulfur, then the oxidation state, it will be 4 because there are total 4 sulfur oxygen bond, and as this is the same atom, that is a bond between same atom, that we will not consider during oxidation state calculation. So in the redox chapter we have Yes, in that chapter we have seen how to calculate oxidation state of any atom in a particular compound. Then it is clearly discussed that sometimes it may happen that if there are more than two atoms in the same molecule. For example, in this case, you have two sulfur atoms in this NR. Now both these sulfur may have same oxidation state or may not have, and that depends on whether their chemical environment is same or not. If it is same, obviously oxidation state will be same, but if it is not same, then it will be different. So as you can see here, if you simply focusing on this formula, forget about the structure, the detailed structure, suppose you do not know it, if you simply focusing on this, then how you will calculate the oxidation state? Overall charge is 2 negative, right? And 2 sulfur. So suppose sulfur oxidation state is X. So I will write 2X. Then 3 oxygen. For each oxygen it is -2. Overall charge is -2. So 2X will be 6 minus 2, that is 4. And X value will be 2. But this is the average oxidation state of sulfur. But if you see individually, that is what is the individual oxidation state, then this sulfur it is 0. For this sulfur it is basically 4. Again you see, if you add 0 and 4 and divide it by 2, because total number of sulfur is 2, then also you are getting the same result. Okay, so the 2 sulfur, what I am trying to say mainly that the 2 sulfur, its chemical environment not same, so oxidation state is also different. Now this is one structure, but here this negative charge it can undergo resonance, and when it is undergoing resonance there will be now double bond between oxygen and sulfur, and any of these double bond can be broken. So I am writing another sorry, it is sulfur, another resonance structure, rest of the part there is no change. Now suppose this negative charge, if it is for making SO double bond, now this oxygen can also carry the negative charge. So this type of resonance, several resonance structures are possible, but if we consider its average structure, then it will be like this. So there will, you can see dotted line between sulfur and all the 3 oxygen, and also the 2 sulfur. There is dotted line. Dotted line means this is basically the average structure. And the total species, it is within third bracket, 2 negative charge total, because in the previous structure the negative charge is directly mentioned on the oxygen, but here as we are considering all the combining all the structure, we have represented it as the average structure. So 2 negative charge, it is within the third bracket, and these 2 negative charge that will be balanced by 2 positive Na plus. So now the structure is clear, and its crystal structure type is monoclinic. There are different types of crystal structure, different names are there. Details you will get in 12th standard, that in the solid state chapter. Once you finish that chapter, you will be able to understand the details of monoclinic. Now we will see how it reacts with different compounds, or if we simply heat it, how it will react. It is true that it is stable compound. You can keep it at that is under normal condition for long days. But if you are heating it, obviously there will be decomposition. After decomposition, you are getting these 2 compounds, and in both cases there is sodium present. So one is sodium sulfate, another one is sodium polysulfite. Reaction with dilute acid. How it is reacting with dilute acid? So in presence of dilute acid, which acid we have taken? Hydrochloric acid, HCl. So there is decomposition. We are getting sulfur and sulfur dioxide. The reaction is called Clock reaction. So Na2S2O3 to HCl, it is forming sodium chloride, sulfur, sulfur dioxide, and water. So 3 compounds we are getting: sodium chloride, sodium chloride, sulfur, and SO2. Reaction with iodine. Now this reaction, you will see its application in redox chapter several times. It reacts, basically it reduces, or you can say reacts, reduces iodine to iodide. Iodine means I2, iodide means I minus. So as if it is feeding electron to iodine. It is widely used in laboratories for titration based on iodine. Whenever you have any titration based on iodine, suppose iodine, it is so first suppose there is iodide. It is reacting with some strong oxidizing agent such as KMnO4. So after oxidation, it is converted to iodine. Then this iodine can again react with this reducing agent Na2S2O3. It is converted to I minus. So this type of reactions we use in redox reaction or in titration. That is very common use is that. So here S2O3 2 negative itself is converted to this type of ion S4O6 2 negative, and iodine, that is basically accepting electron from H2O3 to 1. So this is the reducing agent. Okay, and we are getting, that is, it's two molecules of H2O3, so it is reacting 2:1. That is the ratio. Okay, H2O3 2 negative, it is converted to S4O6 2 negative and 2I minus. So these are the properties. Some more properties we'll also see. Next we have reaction with AgNO3. What we call it? It is silver nitrate. So reaction with silver nitrate, aqueous medium obviously, it reacts with aqueous hypo solution. So aqueous hypo solution is basically another name of this molecule, sodium thiosulfate. So Na2S2O3 reacting with 2AgNO3 and it is forming Ag2S2O3. So this is silver thiosulfate because this part is same. So the term that we use, thiosulfate, that is for the ion H2O3 2 negative. So this part is still same. So you can call it silver thiosulfate. And this is, there will be precipitation, white precipitation. NaNO3 is water soluble, so there is no question of precipitation. Now this Ag2S2O3, it can react with water and ultimately there will be formation of silver sulfide. See, PHIDE, because we have now S2 negative and Ag2S2O3 reaction with water, we are getting black PPT of Ag2S. This is black. This is white. H2SO4 byproduct. Application. Commonly used chemical material as the fixing agent in photography, film, printing, plate making industry. So from the list of uses, you can understand how versatile its uses are. As a reducing agent, this application you have already seen. Used in tanning, where animal skin is converted to, that is, to some usable items. Used as a bleaching agent for removing residual and a mordant in the paper and textile industries. So there are some technical terms for specific industries. We are not going into the details. Approved for the treatment of certain rare medical conditions such as cyanide poisoning, cisplatin toxicity, etc. So these are basically medical use. Okay. And as a dechlorinating agent, dechlorination agent, that means it can be used for removal of chlorine. So that is why we are using the term dechlorination. Whenever you are using the term DE, suppose I am saying dehydrogenation. Dehydrogenation means you are removing hydrogen. Hydrogenation is addition of hydrogen. Dehydrogenation is removal of. Chlorination is addition of chlorine. Dechlorination is removal. So dechlorinating agent and fungicides for drinking water in water treatment. So to make the water drinkable, that is in the purification, it has use. So after finishing all the sodium related compounds, total 5 to 6 compounds we have discussed. First, we have seen the properties section, then preparation section. Second section is properties, and the third section is application part. Biological importance of sodium and potassium. So we are discussing group 1 of S block, and in group 1, remember what are the elements? Lithium, sodium, potassium, rubidium, cesium. Now among these two, when they are in ionic form, that is Na plus K plus, there is some biological significance. These ions are found in large proportion in biological fluid. Now there is specific functions for them. That is Na plus individual, if you consider there are some specific roles. K plus, it has some specific roles. Sometimes there is also some combined roles where both Na plus K plus, they are working together. That also we will see. So these ions perform important biological functions such as maintenance of ion balance, nerve impulse conduction. Now if you see this data, the typical 70 kg man contains 90 gram of sodium, 170 gram of potassium. So see, this amount of these two elements, if you compare with iron and copper, these metals also have some importance in biological importance. But if you compare, requirement is for 70 kg man, keeping this value fixed. Requirement for iron and copper is 5 gram and 0.06 gram. But just compare now with sodium and potassium. It is really very large number. Compared to 5 and 0.06, if now we have the number 90 and 170. Okay. Despite being chemically similar, these two ions, it is true that they are chemically similar because first of all, they are from same group. So you can expect some similarity. They are carrying the same amount of charge, but still they are different element, right? So despite being chemically similar, these ions differ quantitatively in their ability to penetrate cell membrane. So penetration property for these two are not same. And this is actually helping in some biological processes. And also they are having different ability in their transport mechanism, in their efficiency to activate some enzymes. So that is why there will be some properties that are characteristic of Na plus, some properties that are characteristic of K plus. And then you will also see there are some phenomena going on where both these ions are working together. So if you simply consider sodium ions, they are mainly found outside the cell, which is located in blood plasma and in the interstitial fluid. Now, when I'm saying interstitial fluid, don't think that outside cells, then how it can be interstitial fluid. Actually, just outside of cell, that fluid is called interstitial fluid, okay? Which is basically surrounding the cell. That is actually the place where Na plus is found. Now, these ions, they can participate. Look at this three statement. First, transmission of nerve signal, regulating the flow of water across cell membrane, in the transport of sugars and amino acids into cells. Obviously, we will not go into the details because that will be mostly biological thing. But these are the, that is their importance, their role basically. These 3 points for sodium. Now, what about potassium? That we'll see in the next slide. K plus ions are most abundant cation within cell fluid. So this is important difference. When we have seen sodium, then it is outside the present mainly in the outside cell fluid. But now when you are considering K plus, it is inside. This is important difference. Okay. Now look at these 3 points. They activate many enzymes, participate in the oxidation of glucose to produce ATP. And this point is basically, you can say, working together. With Na plus ions, they are also responsible for transmission of nerve signal. So this point is basically common point. And this common point you have also seen in here. Transmission of nerve signal is basically along with K plus. So this first point is common point where it is working together with K plus. And the same thing is also mentioned here. See the last step, working with Na plus. Now how they work with together? It is basically in sodium potassium pump. Though sodium potassium pump in 11th standard details are not mentioned in the syllabus, but we'll just have a primary idea. Na plus and K plus ion participate in the transmission of nerve signal. So this statement we have already seen. So what it actually means, it is the process of moving ions, which ions? These ions across the cell membrane. Now for this process, there is some requirement of energy because it is active transport process. That means it needs some energy. So where from this energy will come? It comes from hydrolysis of ATP, adenosine triphosphate. When there is ATP and there is hydrolysis, there is some bond breaking going on, and after this bond cleavage there will be amount of energy released. This energy will help in this active transport process. So this helps in to provide necessary energy. So here we have very simple picture of the sodium potassium pump. So pump, see, we are using the term pump. So pump, it does what? Just think about normal pump. It forcefully does some things, right? So here also the same thing. As if, see here outside total 3 positive Na plus ions are there. But this is inside of the cell, only 2. This is inside cell, this is outside. And this part, it is basically the membrane, fine, cell membrane. This is the enlarged version, as you can see. Now this is the channel through which these ions can pass. And ATP, when converted to ADP, there is huge amount of energy released, which will provide energy in this process, that is sodium potassium pump. This process consumes more than 1/3 of the ATP used by resting animal. So ATP, its work, that is obviously to provide energy, but not for this process only. There are so many other processes going on inside our body. So ATP has different roles, but resting animal, if we consider, one third is very large part, right? Or almost 33%. 33% of ATP's energy is consumed in this process. This process is responsible for maintaining large excess of Na plus that should always be present outside the cell. As you can see here, it is mentioned 3, but here it is only 2. Excess of Na plus outside the cell should be there for proper maintaining of all the biological phenomena, and large excess of K plus should be inside. Okay, so these should be maintained. Otherwise, that is actually the work of the pump. If this balance is disbalanced, suppose a large amount of K plus is outside and less amount of inside, so it will not work. So this should be maintained. So ultimately what we have seen, Na plus K plus, they have some separate roles, but together also they work for a transmission of NAT signal. Now some problem based on this. Match list with list 1 with list 2. So in list 1 we have potassium, potassium chloride, potassium hydroxide and lithium. Now potassium, what is its use? Look at this, all the terms in the right hand side. It is basically matching with sodium potassium pump, right? Then KCl. Remember, that is not in previous class, maybe previous the 2 or 3 class before we have seen the use of all the alkali metals. So in that part you can find in that particular slide that use under the heading of potassium, that KCl is used as fertilizer. So this is already discussed in the, you will find it in the uses part of alkali metals, group 1 metals. So KCl is basically acts as fertilizer. Then KOH is basically absorbent of CO2. Carbon dioxide it can absorb. This is a specific property. So C is matching with 4. Now simply if you are sure about that A is 3, B is matching with 2. These 2 is enough to choose the first option, isn't it? So K plus sodium potassium pump, though here K is mentioned, but it is actually working in the form of ion. KCl is fertilizer, KOH is absorber, lithium is used in thermonuclear reaction. So this should be the correct option. C is 4, D is 3. So this question is related to washing soda soda ash, number of water molecules in these two species, washing soda, soda ash. Remember, both are having same chemical nature, Na2CO3. Sorry, Na2. But when we are calling it washing soda, then it should be 10 with 10 water molecule. But when we are calling it soda ash, it is basically simply with no water molecules. There is no water molecule. So it should be 10 and 0 respectively is there. So for washing soda it is 10. For this is 0. So last option is the correct option. Product which is not obtained during the electrolysis of brine solution. Now we have used this process, that is electrolysis of brine solution. This is already discussed in Kastner-Kellner cell. So in Kastner-Kellner cell, when we are saying electrolysis, obviously there will be cathode, there will be anode. So specific reaction is going on in the anodic section, in the cathodic section there is separate reaction going on. So to answer this question, basically you should have the idea what are the reactions going on in the Kastner-Kellner cell. It is not directly mentioned in the question that it is Kastner-Kellner cell reaction, but actually when we are talking about electrolysis of brine solution, this name, this is the name of the cell we use. So look at these reactions. At cathode, what reaction is going on? At cathode, as we know, there is reduction. So here Na plus ion, that is accepting electron, and it is reduced to sodium. So this is reduction. At anode, there is oxidation. So Cl minus ion. Now, if you are thinking where from Na plus Cl minus coming, it is coming basically from brine solution. Brine solution is nothing but saturated NaCl solution. Now, NaCl solution means what? There will be Na plus, there will be Cl minus. Brine solution, water is obviously there. So this Na plus, it will accept electron at cathode and it will be reduced to Na. Now, as there is presence of mercury, so that is why it is not simple sodium, because simple only sodium, if it is in water, there will be explosion. So it is in the amalgam form, combined with Hg, mercury. So it is not only sodium, remember that. So it is reduced form now, and where from this electron coming? This electron is coming basically from this reaction which is taking place in anode. So in anode, Cl minus is donating this electron, itself is oxidized to chlorine. For balancing purpose, it is written as half chlorine, so that both sides there is only one chlorine. So these are the reactions going on cathode and anode, but this sodium amalgam ultimately reacting with water, it is producing NaOH. So in this way, we can make sodium hydroxide. Now, if you overall look at this, all the processes, and look at the question, it is asking the product which is not obtained during this electrolysis. Option C, NaOH, obviously it is produced. Chlorine is also produced at anode. Hydrogen is also produced when sodium amalgam is treated with water. That is reacting with water. Then also hydrogen is produced. So this is product, this is product, this is also product. Sorry, this is also only this one we are not getting. So this is the product we are not obtaining during the electrolysis of brine solution. So this option is correct. Next problem. Correct statement or statements means maybe more than one. So you can see there are total 3 statements. 1, 2, 3. With respect to potassium ion. So all these 3 statements, they are related to K plus. That are abundant within cell fluids, is or are. Depending on if it is single statement, suppose you are choosing option D, then it is only one statement, third statement is correct. In that case, it is, otherwise it is are. But all are related to potassium ions that are abundant within the cell fluid. We have just discussed it, that sodium is always in the outside part. Inside part there is K plus, which is abundant. So what statements are mentioned here? They activate many enzymes. This is true. They participate in the oxidation of glucose to produce ATP. Now this statement directly in that is the slide where we have discussed, probably I have not mentioned it, but they also participate in the oxidation of glucose to produce ATP, and along with sodium ion, they are responsible for transmission of nerve signal. So these also we have seen. So all the statements are basically correct. Fine. Same statement is also written in the box. So what we should choose? We should choose option C, 1, 2, and 3. Solve a process related problem. It is saying that sodium carbonate can be manufactured by Solvay process. Remember, we have used this process, right? But potassium carbonate cannot be prepared. Remember, what this information I have already given, that potassium carbonate you cannot make by in Solvay process, and there is a particular reason for this. So that reason you have to choose from these options. So what is the actual reason? K2CO3 more soluble, K2CO3 less soluble, then potassium bicarbonate more soluble than NaCl3, potassium bicarbonate less soluble than NaCl3. Now again we will see all the reactions. So this we have already seen during the discussion of Solvay process. Remember, there are total 4 steps we have seen. Now specifically in the third step, there is formation of NaCO3. Now it has very less solubility in water. As a result, you can get PPT. You can filter it out and you can use it after filtration. You can use it in the next step where you are simply heating it. You are getting the final desired product. Now, if you want to apply the same processes for the preparation of K2CO3, suppose instead of Na2CO3, you want to make K2CO3, then you have to that is in this third step, obviously what you will get, instead of NaCO3, now you will get KCO3, right? Now when you are getting KCO3, unlike NaCO3, it is now more soluble. Now more soluble means no PPT formation will be there, and that is why you cannot use Solvay process for the preparation of K2CO3. We can't do so, we cannot make. So the reason is KCO3 is more soluble, and that is why we cannot get PPT, we cannot filter it, and the next step we cannot proceed. So it has nothing to do with K2CO3. That is the final product. We have to, that is any one point between C and D, but not D. KCO3 is, if it is less soluble, then it will actually help us to easily, there will be PPT formation, but that is not the case. It is more soluble. Okay. Now this problem is also related to that is you need all the same equations that we have just seen in the Solvay process. It is just that the question is designed in such a way to make it a little difficult, but if you read it carefully, you will see it is actually the same reactions the problem is talking about. The white PPT Y obtained on passing colorless, odorless gas X. X is colorless, odorless. So when X is passing through an ammoniacal solution of NaCl, that means NaCl, ammonia, water is also there, because when we say solution, you can mention it or not mention it, but NaCl is there, ammonia is there. So you are treating this colorless, odorless gas with NaCl ammonia, you are getting Y. Read the step, that is line, very carefully, because it is mentioned in a very complicated way. The white precipitate Y you are getting when you are passing this X through ammoniacal solution of NaCl. Ammoniacal solution means ammonia is obviously there. So when you are treating it with X, you are getting Y, which is white PPT. This white PPT loses about 37% of its weight when heated and white residue Z is obtained. Now in another reaction, why you are hitting Y, you are getting Z, which is having, and that is it is white and it has basic nature that is mentioned in the question. So you have to find X, Y and Z, right? Now if you look at the options for X, there are total 3 gases N2O2 CO2, all of them colorless, odorless, fine, but N2 and O2 obviously not correct. Okay, it is basically carbon dioxide and the process is basically Solvay process. So see, same reactions I have again mentioned here. NH4 HCO3, how you are getting it? You are getting it from, sorry, not this one, let me again tell you, NaCO3 PPT that you are getting, that is basically Y. Now how you are getting Y? You are taking help of these reactions, but actually the main component that you have taken, NaCl, that is the source of sodium. You have taken ammonia, you have taken CO2. Water is obviously there. Then this ammonium carbonate obtained, then this ammonium carbonate, in the next step ammonium bicarbonate. But ultimately this ammonium bicarbonate and carbonate is not mentioned in the question. The question it is mentioned that X, the odorless and colorless gas, that is treated with ammoniacal NaCl solution. That means it is just focusing on NaCl and ammonia, as if these two are the main starting material. This one, and CO2 is actually X. So when these three together, you are getting NaCO3, which is basically Y. And this Y, when you are hitting, you are getting Z, which is white again, and it has basic nature also. So X is CO2 that is present in both C and D, but Y is not NH4HCO3, because NH4HCO3 is here. And when, if you think that it is Y and you are hitting it, obviously you do not get Z. So it cannot be Y. Y is sodium bicarbonate, not ammonium bicarbonate. So this is Y and this is Z. Okay, so basically to answer this question, if you do not have prior idea about all these details of Solvay process, then we will not be able to answer it. Okay, so that's why these equations are so important. This is the correct option. Now we are end of the session, and also we have finished group 1. So next day we will start group 2 elements, that is alkaline earth metal. So alkali metals group 1, that we have completed today. So we are ending the session here. Thank you for listening.